What's going on, class? I'm KG. Today we're going to be teaching about universal gravitation.
He actually meant to say, why Newtonian physics break down into black holes.
Let's say that these two balls are the Earth and Moon, right? Obviously, in the real world, they're much bigger. But for now, this gives us a simple way to understand the basics of gravity. Now, the strength of that pole depends mainly on two things. First, the masses of the object. The larger the mass, the stronger the gravitational pull. That's why Earth's gravity is much stronger than the Moon's, because Earth is much more massive. So in short, mass is directly proportional to gravity. Bigger mass, stronger pull. Second, it depends on the distance between them, specifically the distance from center to center, called the radius. Here's the twist: gravity is inversely proportional to the square of the distance. That means that the distance between the object gets smaller, the gravitational force doesn't just increase, it increases a lot. So as the distance decreases, the pull between them grows stronger and stronger. Yo, Aaron!
Thanks, Caden. At this point, you might be wondering, if gravity is pulling objects together, why don't planets orbiting an object just get sucked straight into the object? To answer that, first we need to introduce the idea of centripetal force. It all ties back around to Newton's first law of gravity. Newton's first law states that an object will continue moving in a straight line at a constant speed unless acted upon by a force. This natural resistance to change is what we call inertia. Now imagine a planet moving through space without any forces acting upon it. It would just keep going in a straight line forever. But when gravity pulls on it, instead of letting it continue straight, it constantly nudges the planet inward, changing its direction bit by bit. This pull inward, this constant change in direction, is what we call centripetal force. Gravity acts as a centripetal force that bends the planet's path into a curve, locking it into an orbit instead of just letting it fly off into space or crash into the star. Alright, Seb?
So why can't we explain black holes using universal gravitation alone? The problem comes when we look at the math. As you get closer to a black hole, the radius decreases, so the gravity becomes stronger. But if you keep following the formula, you'll eventually reach a point where gravity becomes infinite. But infinite gravity doesn't make sense in the real world. There's also a major flaw in Newton's approach, but Einstein's theory was a fix for this. Gravity was no longer the theory of an invisible force of attraction between two objects of mass. He predicted that it was an alteration to space itself. He made predictions that light would be affected by gravity, and this turned out to be true in his predictions that were tested during solar eclipses. We saw that light bends as it passes near massive objects, meaning that objects travel a path within space. In other words, gravity isn't a simple force between two objects. It's a distortion that creates curves in space the objects will follow. This is why planets orbit, why light bends, and why black holes exist. Okay. Here we have a simple diagram to represent Einstein's theory of general relativity. This orange in the middle is representing a star, right? And what it's representing is how mass will be bending space. And as you can see, it's creating kind of like a well. The more massive an object is, the more it's going to be bending space, the fabric of space, right? And as it's bending it, it's creating little curves around here. As we throw these marbles, they're going to be moving. And obviously going to move towards here because gravity's going to be pulling them down. But in space, they're going to keep traveling and traveling along. That was a bad example, but they're going to keep traveling along these curves, and that's how they orbit. That's how they orbit around these planets and around these stars. But black holes are a different case. Since they're very dense and way more massive in the single point, they're going to be bending in space more and more until they create a hole in space. Before general relativity, black holes weren't a thing. But with Einstein's equations that predicted that with enough mass, a star or another object could bend space-time so deeply that it would create a plane where not even light could escape, a black hole. This theory made sense because with enough mass, in one place the distortion in space-time would be so extreme that it would appear like a hole in the fabric of space. And of course, Einstein's prediction turned out to be correct. In 2019, scientists captured the first ever image of a black hole, proving that black holes were real. Today, general relativity is the widely accepted explanation of black holes, especially when we're talking about the extreme gravitational fields such as black holes.